So let's just go ahead and do some examples, and we'll try to go backwards from the gradient. So let's say the gradient of f is 2x comma 2y. And the question is, find an f that satisfies this. All right, so I know that my partial derivative with respect to x has to be 2x, and my partial derivative with respect to y has to be 2y. This appears pretty easy, so if I'm constructing an f, partial derivative with respect to x is 2x, so if I just put in an x squared and then nothing else affects it, I'll be okay. And if I put in a y squared and nothing else affects this guy, I'll be okay. So I can maybe just guess and then check. Let's see, the partial derivative of f with respect to x is in fact 2x, and the partial derivative of f with respect to y is in fact 2y. Okay, so this one was pretty easy. I got it correctly just by guessing. Maybe let's do a different one. Maybe we'll reverse them. 2y comma 2x. So what happens now? My partial derivative of f with respect to x is 2y. So if I'm constructing my f, I'm going to want a 2xy in there. Because if I take derivative with respect to x, then 2y is a constant, so I'll leave that there. And now, is that going to work? Because that's going to mess with my partial derivative of f with respect to y. But actually, it messes with it in the exact right way, because if I just take what I have here, take the partial derivative with respect to y, I'm good. I have 2x. Okay, so that was a happy coincidence. That was maybe even easier to guess. Okay, what if I have a little bit more complicated? Now I have 2x plus 2y, comma 2x plus 2y. Okay, now my partial derivative of f with respect to x is 2x plus 2y. So if I start constructing my function, I'm going to want x squared plus 2xy plus maybe more stuff that hopefully doesn't depend on x. And then if I start checking my fy, which also needs to be 2x plus 2y. Okay, so the first term doesn't depend on y, so it won't affect my fy. The second term, 2xy, if I take partial derivative with respect to y, I'm going to get 2x. So that part's actually taken care of. So I just need to create this 2y, and that's actually pretty easy. I'm just going to put a y squared here. All right, and we can check this. Partial derivative with respect to both things, with respect to x, we get x squared, or we get 2x plus 2y, and then with respect to y, I get 2x plus 2y. And actually, maybe it's even easier to see now that I've done it if I write it as x plus y quantity squared. Because then my partial derivative with respect to each one, I'll just use the chain rule, is going to be 2 times quantity x plus y, which is certainly what I have up here. Okay, so those were all good examples. Maybe I don't have a great method yet because it's guess and check. And maybe if the problems got harder, I would get confused. So let's do something else. Let's do, say the gradient is y comma 2x. Okay, so let's see, I need my fx to be y. So if I start constructing my function, I'm going to need at least one term of it to be x times y. And then I'm going to need to add, actually for my partial derivative with respect to x to be exactly y, I'm going to have to add a function g that only depends on y. There's got to be no x's in here. Otherwise, the function g is going to mess with my partial derivative of f with respect to x. Okay, let's look at partial derivative of f with respect to y. That's got to be 2x. Let's just take the derivative, take the partial derivative with respect to y. I'm going to get x in the first term and then g prime of y in the second term. And we said that had to be equal to 2x. So if I just solve for g prime of y, I get x. But this is a problem because I said there's no x's in g of y. So how did an x show up in g prime of y? And actually, like, if I went back, then g of y has to look something like x, y. Maybe it's plus a constant, but like now it's got x's in it. And what happens is I'm wanting my partial derivative with respect to y wants f of x comma y to be 2xy is basically what's happening. Because if I took the derivative of this with respect to y, partial derivative, I would get my 2x back. But my partial derivative of f with respect to x wants my f to be just xy. So they're in conflict. So here, actually, no f exists that has this gradient. And in some cases, you'll get that. F gradient of f equals y comma 2x. Okay. And we're going to define, so this is, the gradient is a vector. And it's a vector with variables. So we call that a vector field. So like, let's say, actually we'll start from scratch so it doesn't look like part of the example. Let's say f equals the gradient of f is a vector field. But maybe like we don't know that it's the gradient of a function yet. So just f is a vector field. If there exists some function, some scalar function f, right? The little function was a scalar function. We always found it was just a normal function. It takes numbers x and y and returns a number. The big F takes numbers x and y and returns a vector. So if there exists a scalar function f such that the big F is the gradient of little f, because the gradient of little f is a vector, then we call big F a conservative vector field. And these are going to be important because these are the ones where we can go backwards. By definition. The definition is that we can go backwards.